Hello, students. Like I said in class, what I want to do today is to give you a lecture on work. When we consider work in a calculus sense, we think about a variable force over a certain path. Now, when you take calculus 3, you will consider paths that are termed curves, and they may take on many different forms. But for now, our path will just be linear. That is, it will be a straight line. And so we want to see how the use of the Riemann sum and then the Riemann integral can allow us to calculate work in the physics sense. Now, your book covers many types of examples of work, and we will cover several of them. But just remember, as you take engineering and physics classes, you will discuss work in other areas having to do with chemistry and electricity and mechanics and things of that nature, which will be more varied. But in the math class, we'll give you the foundation of that so you can go into the other areas and have a level of confidence. So first, what I want to do is share the screen just to give you an idea of the calculus that's involved. And of course, this will look very usual to you. You noticed when we talked about area, we talked about volumes of solids of revolution, we talked about arc length, and the area of a surface of revolution. Those all depended on the integral and the same derivation in order to justify a definition. So what we want to do here, and I've gone ahead and written this out to give you some idea about how we would structure work within the confines of a partition. So as I said before, when we think about a variable force, for now, we will apply along a linear path. So I guess when you think about work, you think about force applied over a particular distance. And what we'll do is just say that our path is defined by a closed bounded interval A to B. And also, we will consider a partition of that interval. Now, as I said before, we're thinking of the product of force over a distance, or the product of force and distance. And so with each type of example, we will need some knowledge of how to determine the force. With the ideas that we will be talking about, we will use Hooke's law, which you probably already know about. We will utilize basic acceleration due to gravity, weight, and also we will use weight as a means of computing the work to move liquids around. So just remember, as you change the scenario of the situation, the computation of force may vary, like the gravitational law, Coulomb's law. All of these laws have been determined in the laboratory. And so how you calculate the force or the variable force has to do with the particular situation. So in general, we just think of force as just being denoted by the letter F, which is unfortunate. So if I use a big F, it will have to be a big G for an antiderivative. And I'm sure I'll just use the F twice and be ambiguous about what the F means. But what we want to do is to apply the force for a particular subinterval, the ith subinterval. And so we have the product here where we have evaluated the force at some element in the ith subinterval, just like we always do. And of course, we assume that F is a continuous force. That is, we will be able to do the Riemann integral. Now, there will be other instances where F will not necessarily have the continuity, but that will not preclude us from doing a Riemann sum. We will have adjustments that we can make. And so that will come not too far down the road. So what we do now is think of, if we sum all of these particular contributions to work on each subinterval, as we do here, and let the norm of the partition go to zero. Normally what we think of that as n going to infinity, when it does mean the same thing, doesn't always. This will give us the integral. So we think about work as being an integral of the force over an infinitesimal distance. And this summative process is basically the limit that we apply. It's the calculus, so to speak. And again, just like when we did the previous problems, we'll go through the process of setting up the integral in a step-by-step procedure so that we're confident that we have something that makes sense. Now, let me just remind you, and I have an example here that will be something that will be important to you. We don't change anything that you already know. For instance, if the force is not variable, we don't need the integral. We just multiply the force times the distance that is traversed. So constant forces do not present any challenge to us. And if we have a problem that combines the two, then we have to make sure that we separate the two categories and apply the correct mathematics in each case. So let's look at that. I have an example here. And I want to go through these. I've got several examples, and I picked examples from notes that I've made, and then also notes that I've just written, basically in the style that I've been teaching. Now, for instance, sometimes, as you'll notice, the notation will be a little bit different, and I will add some explanation to that. Now, what's good about this example is that you're going to see the type of algorithm that we apply when we compute work. So here's a very simple question, but something that is actually very realistic. We have a 50-foot chain that weighs 4 pounds per foot. Okay, lots of times we will have a linear density or an area density or a volume density in the problems involving work. And this particular chain hangs from a winch that is 50 feet above the ground level. Also, a 500-pound load is attached, as I've drawn here in my schematic. Compute the work to retract the entire chain. So if you have a machine that you click on and it starts to retract the chain, the load goes up and takes it all the way up 50 feet. Okay, well, one part of that problem is very simple. The other part requires calculus. So let's just look at this. Notice here what I've done is I've broken the problem down into two categories. One is the chain and one is the load. Let's just go ahead and look at the work for the load. That's the simple part, because the force of the load does not change. It is non-varying, so to speak. So it doesn't get heavier or lighter, so to speak. We're only thinking about staying close to the earth. And so this 500-pound weight is moved a distance of 50 feet. Okay, so we simply take the product of those two numbers and get 25,000 foot-pounds. That's it. So that's a constant force over a prescribed distance. Very simple, something you already know how to do from the elementary physics that you've taken at your high school. Now, when we think about the chain, as you retract the chain, there's less of it, okay? So the gravity that's acting on the lesser part of the chain produces a smaller force. So the idea there is that the weight of the chain varies as you retract it. Okay, so how do we compute that? Well, one thing we can notice here, and this is usually my technique, is to say, let's go ahead and set this up as a problem in the Cartesian coordinate system. So if you like, you can put your X here and your Y here. And we'll just go ahead and use Y as the vertical distance. So we've got our setup here where we take Y in the interval 0 to 50. Okay, so you've got that point. And then what you want to do is think about taking a little sliver there. Notice I've written this as a delta y, that little piece of the chain. And then you say, well, what is the distance that piece would have to move if we were retracting the chain? Well, again, you can simply notate this as a distance strategy that we've used many times. So to go all the way to full retraction, we have 50 feet. But notice we're starting here at y, as we've taken y here, and the distance to the point 50 feet will just be 50 minus y. So that will be the distance that this piece, delta y, will have to move in order for the chain to be fully retracted. But then, of course, we have to do that for all the possible y's, and of course, there are uncountably infinitely many of those. So what we do, and here's a strategy that I think helps. I think about length, I think about the force, and then the work for that little piece. So we're thinking like sub-interval, but we're being a little bit more casual just to make the process simple. So I'm going to look at the delta L as being the delta Y in this case, since this is just linear, this is a chain. We're not looking at an area or a body. And then how do we determine the force? Well, again, we go to the constant force, constant distance. So we know that the chain is 4 pounds per foot. So we simply multiply the constant force times the distance moved. So that infinitesimal distance it moves is delta y, and we multiply that by 4. So we have the delta F, so to speak, for delta y. And then, of course, you see we're just building the delta W, which is the work to move this particular piece, delta y, to full retraction. And so we simply multiply delta F by the distance moved, which is 50 minus y. And of course, that distance will be the same for any y that we take here. So just like we've done before, and again, you can be much more formal in this derivation, but it's really not necessary. The idea is to have a setup to move you to the integral in a way that you feel confident. So now when you look at this, you can now say, well, our interval of integration is 0 to 50, and then we just place all of this into the integrand. Of course, the delta y becoming dy, and then the 4 and times the 50 minus y being the other part of the integrand. Now notice here, what I've done is simply done a visual. I factored the 4 and I've done the antiderivative. But here's one thing you can also do, and this is what I've been doing in class. If you like, let me just go ahead and write the integral here. You get the same answer, but I just want to show you how I've been doing it up until this point. And again, there's nothing wrong with the method I've used here. As I've said many times in class, I like to vary the method to make sure that the student feels confident and that you can easily check your work. So now, since we've used linearity to factor the 4, we can just focus on the 50 minus y. So if you like, you could do a big G. And of course, I'll use G instead of F since F is already taken. So this will be a 50y. And of course, it's going to look just like that, but I'm going to manipulate it a little bit, and then a y squared over 2. So this is certainly a way to do it. But as I've been teaching you, I'm thinking that sometimes it's easy to manipulate the most general, or not the most general antiderivative, just an antiderivative to make the evaluation simple. So first, let's factor the y. So we get 50 minus y over 2. And then we can do a common denominator of 2. So we get y divided by 2. Multiply the 50 by 2 gives us 100 minus y. So this can be a point of evaluation. This is another way to do it, which I find to be very simple. And I'm always looking for ways to make the process easy. But again, as I've said many times, the method you choose is one that you feel most comfortable with. But now, when we look at this, the evaluation is simple. We can say, okay, G of 50 Again, remembering the 4 is still there and we will use that. We'll multiply this difference by 4, but just using the method I've taught you. G of 50, very simply, we get 50 over 2 and 100 minus 50. Okay, well, that's easy. 2 into 50. And again, you're thinking, can we just go ahead and hold off on that? Well, it won't matter. That'll just give us a 25. And then, of course, the 50 from 100 is just 50. So now, of course, 5 times 25 is 125, and add a 0. So we've got that. Now let's go ahead and do G of 0. Well, the beauty of this method I've been teaching you is that G of 0 is just clearly 0. So that's easy. So now we can go back here and we have 4 times, again, the difference, G of 50, minus G of 0. So all that's left, clearly, this being 0, is just the 1250 times the 4. So we have 4 times 1250. Now, another thing that's easy to do, again, 4 times 1,000 is 4,000. And of course, 4 times 250 is 1,000. And that gives us 5,000. So what we see is the variable part, that is retracting the actual chain, requires a work of 5,000 foot-pounds. And then, of course, just pulling up the load with a constant force requires 25,000 foot-pounds. So this implies that the work will just be the sum of the two. So we have 25,000. Now, of course, you don't have to put units in the calculations. I know your physics professor would not be happy, but you can just include them at the end in 5,000. And that gives us 30,000 foot-pounds. So you see that as you work through, and I've noticed on your papers that some of you use a combination of this. I do, however, recall in the past that your calculations are usually much more correct when you have a method that you can easily check. Now, with that said, as you notice here, I just did this in a linear fashion using the vertical line, which is fine. Again, when I taught you this, we made the comment that you can use this or you can use this method or a combination of the two. But I like this example basically because it connects to the process that we already had been doing. Like I said, the important thing is the concept of finding the volume of a solid using cross sections. Okay, it's not necessarily a force that's going on, but it's a summative process, which is very similar to what we're doing here. The only additional part of the problem is looking at the actual piece of the object that we're moving, applying the force. Okay, how do we apply the force correctly? That is, with that piece and a particular force, we have to also add the factor of the distance. Remember, work is force over a distance, the product of force and distance. And so the elegance of the physics is communicated through the elegance of the mathematics. So again, very simple problem, but a very important problem. Now I have several examples that I want to go through where I have used the method I have been teaching, and I want to summarize them. Now, I've taken these from your homework, so you can look at these and use them as you need. Just remember, Every time you do a problem, you simply want to set up the problem, get practice with the algorithm. That is, do it enough times so that you feel comfortable with the process, and so that when you test, you are confident and you move through the problems efficiently and accurately. Now, here are two very simple examples, but very important ones that I want to go over. The first one is as follows. It says we have a force of 450 newtons stretches a spring. Okay, you're thinking, wait a minute, this is not, gravity here so much. You got a spring. So how are we going to calculate the force? Well, that's going to be Hooke's law, and it's very simple. And so what we want to do is compute the work to stretch the spring from 40 centimeters to 70 centimeters. Now, this is important. Hooke's law, this is not written as a vector equation. So don't get all upset that, oh, well, it didn't look this way in our physics class. Well, when we do calculus 3, we will have more attention to vectors, but what we're looking at here is simply a magnitude. We are not doing these calculations where we're considering direction. Force is clearly a vector, okay? But I'm not talking about vectors. I'm simply here in this process looking at magnitudes. So to get more formal, when you do the physics, you will be associating a direction with the vector that you're dealing with, and that vector will be force. Now, one thing about Hooke's law is that when you apply a force to a spring, the direction of motion and the force will be opposite of each other, okay? And so that's where students will say, well, where's the negative? Okay, when you write the vector equation, there will be a negative, but here we're only concerned with magnitude. So just keep that in mind. In physics, you'll be a little bit more attentive to the concept of vector. So as I've written here, we have force is equal to a constant K times the distance x. So F is Kx. And K is simply a constant that has to be determined. So we just have to be given enough information to determine it. So when you look at this, we see that the spring is stretched 30 centimeters when the force of 450 newtons is applied. And of course, our units here will be Newton centimeters, which is a little bit odd. We usually do the Newton meter, but again, this is the way the problem is written. And the WebAssign didn't seem to have an issue with the mixing of the units, but of course your physics professor would probably prefer the meter there. So what we do at this point is we simply apply Hooke's law to determine the constant of proportionality. So we have 450 equal to K times 30. Of course, the zeros absorb, and we just have 45 divided by 3 to give us 15. Again, you can apply all the units here, but I'm not going to require you to do that. Just remember that in the physics class, your professor may require you to write the units, and certainly that would be a good thing to do. So if you want to get upset with me about not applying the units, you can do that. So now what we can see here is we have a way to write the force. What does this mean? Oh, of course, the light goes off when there's no motion in my office. So the force, or variable force, will just be 15x. So the computation here is very simple. And so when we apply the definition, we simply integrate the force 15x from 40 to 70. Again, just for simplicity here, newtons applied over centimeters, which again is interesting units there. So what I've done here is I've written this the same way as we've done in the past. An antiderivative will simply just be x squared over 2. Notice I factored the 15. So now very simply, we don't even have to do these separately. These are going to be very easy to do. We'll have a G of 70 and a G of 40. Well, if you like, you can go ahead and factor the 2 here because it's common to both. And then we just have a 70 squared minus a 40 squared. Now, of course, that's just a difference of 2 squares, which, of course, we have to worry about that in a very number theoretic way. So notice when we square the 70 and the 40, we get 100 in each case. So we can go ahead and factor the 100. And then of course, we're just left with 7 squared minus 4 squared. And so of course, that's a difference of 2 squares. So we get 7 minus 4 times 7 plus 4. So very simple numbers. Okay, of course, now the 2 absorbs into the 100 to give us a 50. We have a 15 times 50. And then, of course, we have 3 times an 11. So that leaves us with what? 5 times 15 is 75. So we have with the 0, 750 times 33. And then you can just break this up to a factor of 3 and a factor of 30. So we'll get 22,500 plus 2,250. And then, of course, when we add these numbers, which you can easily do, we have 24,750 Newton centimeters. So again, the calculation is very simple, and I want you to see that it's just exactly what you've been doing. So Hooke's law will simply be a way of computing forces when you're dealing with springs. And again, remember, this is dealing with springs in such a way that you don't mutilate them. You know, Einstein went to the extremes. He had to modify Newtonian mechanics for extreme situations. So don't get Einstein on me. Just stay within certain parameters so we can still apply Hooke's law. Now, another example from your homework, which I found to be very interesting, was the following. This is interesting because you notice with the homework that many of the parameters get varied. And so as you do your problem, you may have a different amount of energy here. This number might be changed. It will vary. So what is the difference with this particular problem? Well, let's read it. It says 8 joules, that's work, is required to stretch a spring 1/2 meter from its natural length. So we would think if we were measuring the way the spring is changing in length, we'd say the natural length can correspond to an X value of 0. And then as we stretch, that would be positive. So we can basically normalize the situation by saying that the spring at rest or in natural position will correspond to a distance of 0, just to make the algebra simple. And so we want to compute the work to stretch the spring an additional 1/10 meter. Okay, we know the energy or the work required to stretch 1/2 meter. So then you're thinking, well, what is that going to do for us? Well, that's going to allow us to determine the force, and then we can compute the actual amount additional to get what we need. So again, it says compute work to stretch the spring an additional 1/10 meter. So if we know what K is, we know what the force is, and then we can apply the same procedure we did to the last problem. So first, we have work, which is 8 joules. Again, you don't have to write in the units here. As I've said before, this will be by Hooke's law, the integral from 0 to 1/2. Again, we take X to be 0 as the base point. The upper limit 1/2 meter, Kx, or the force over a distance. So we have Kx dx. Now here we just simply integrate. Now, one thing I've noticed here, and I did this one kind of simply, if you think about this, this is the same problem. Here, instead of factoring the 15, we just factor the K, just like I did here. And the big G, I had to go back and write it as a G. I think I probably wrote it as an F. Is just X squared over 2. So now we do the same thing here and think about, okay, well, we've got G of 1/2 and we've got G of 0. The G of 0 is clearly 0. So we have 1/2 squared times 1/2, which gives us 1/8 times K. So we have K over 8 is equal to 8, cross multiply, and K has a value of 64. Now, another thing that we want to do here is simply take this to be able to write the force. So we can just write this extra here. The variable force will just be 64x by Hooke's law. Again, we're just looking at magnitude. We're not looking at the vector equation. Just remember that. So now we think, okay, well, what's our base point? Now the base point is 1/2, but we want to move an additional 1/10 meter. So let's see what the upper limit is. Let's just add the 1/2 and the 1/10, get a common denominator. We get 6 over 10, if you see here. And now you might be thinking, do we want to reduce this? Unreduced, look what I've written here, unreduced limits, easier evaluation. So you look at this and say, well, you know, I've got a 5/10 here. Maybe I'll just leave it as 6 over 10 and avoid that. You can always make these determinations as you work through. So I just kind of backed up a little bit and used 6 over 10. Now we have the same situation going on. We've got the same big G. We have the 64 factored. So now we just have to square the 6 over 10 and we have to square the 5 over 10. Now, one thing that you'll notice here, which is kind of interesting, and notice here, I've got my 1/2 here, but I need to put the 1/2 right here also, because that's part of the antiderivative. So I'll just do this like this, kind of like we did up here. So again, we got the G here is the x squared over 2. So now notice what I've done. I've done the same thing again. We've got these, and G of this is 6 over 100, 6 over 10 squared, and G of this is 5 over 10 quantity squared. So what's that going to give us? It's going to give us downstairs a 100 in both cases. So you can go ahead and factor the 100. Notice the 2 1/2 just runs down here. And so we've got 64 over 100. And then, of course, 6 squared minus 5 squared, difference of 2 squares. So we get 6 minus 5 times 6 plus 5. Well, that's real simple. And now, of course, 2 into 64 gives us 32. So we have 32 over 100 times 11. Okay, well, that's pretty simple. So now what we can do is just go ahead and reduce this. No need to do any extra work here. Both of these are clearly divisible by 4. 4 divides the 32 to give us 8, divides the 100 to give us 25. Of course, the 4 is absorbed. I didn't write that out, but I think you can see that. And now, very simply, 11 times 8, we love to multiply by 11. We get 88 over 25 joules. So this is an interesting problem. Simple, but again, showcases a lot of the very important strategies that we use. When you're working with these kinds of problems, you got your pi with the disk method, you've got the shell method, you got the 2 pi, you've got the area of a surface of revolution, you have another constant of 2 pi. You've got all these numbers floating around that are just easy to overlook. So again, when you break down the strategy, even though it's very simple as it is here, it's easy to check and to go through, because a lot of times I'll be working and I'll just, oh yeah, I need this 1/2 here, but then I don't go back up and put it in the original equation. So again, just realize here that all we have to do, say like if we compare this to another method, if we're doing arc length, we got to look at y prime, we got to square, we got to add 1, then we got to square root it. That's the algorithm. Here, we're just simply focused on trying to figure out what the force is. Once we have the force, we could write down the delta W, and then we're done, okay? And then, of course, what's the last part of the problem? Computing the interval, which could probably take more time than setting it up. It just really depends. How meticulous do you want to be? So now what I want to do is to look at an example that utilizes moving liquids. And this is a personal favorite. These always end up on the test, but they're important. And they actually are relatively interesting. When I say that, I say interesting because they remind us, kind of like we were doing the chain, with the piece of the chain, our delta Y, and determining how that enters into the Riemann sum as we compute the work, determine the force, and then of course get the work for that particular strip. We're going to do the same thing for moving liquids. Now, when you're doing a problem with water, you've got your English units and you've got your metric units. When you're working with an English system of weights and measures, what we call it volume density, so to speak, for water is 62.4 pounds per cubic foot. So what I usually tell my students is just write that as rho, as just a Greek letter, and then you can substitute at the end to get the number that you need. Now, of course, WebAssign may say calculate exactly, no approximation, or they may say round to a certain number of decimals. We always know that we just go to the exact, and then if we have to substitute some numbers, like we're substituting 3.14 for pi or whatever, we make sure that we don't truncate things. But again, we're taking this to be a constant and given with no extra. You know, we often struggle anytime we see a decimal. We think that's an approximation, not necessarily. Here we're taking this as a constant, okay, and that's how it needs to be perceived. So what we do here is just like when we're working with volumes and cross-section methods and things of that nature, the geometry is the linchpin, so to speak. Do we understand the geometry of the solid? And if we do we understand how we can set up the volume calculation? Now, of course, with cross sections, you have to understand the area of the cross section, or at least in as much as you can set up an area formula for it. So when you're moving liquids around, the tanks that will be involved will be geometric objects that you understand. So let's look at this particular example. Again, we have a rectangular tank. We've got a base that is 4 feet by 5 feet, as I've notated here. We have a height of 4 feet. The tank is full of water, okay? Water is pumped to the top, so we look at this idealistically. Water is moved to the top of the tank, so to speak, and after that, you know, you can throw it off to the side, or maybe it drains into another tank, whatever. Don't worry about that. Just notice that we're moving water to the top of the tank. That's it. How that's done is a problem for the engineers. Okay, that's a problem for the artist in residence, so to speak. We are working a math problem, so how that happens, again, that's for someone else to do. We're going to look at this from a mathematical standpoint, and then the engineers can say, okay, the computation is this, so we should expect to expend this much money for the energy supply to do this particular task. So keep in mind what we're doing, and then of course what some of you as engineers will have to do in addition when you're on the job. So it says water is pumped again to the top edge of the tank. Compute work to empty half of the tank and all of the tank. Okay, well, this is not a hard problem. Just like the last one, we just need to figure out how to set this up in a way to compute the work for some piece of the water in this tank. Now, how do we think about this? Well, again, this is where a little schematic is very helpful. And of course, this is very simple and not very detailed, but certainly has enough detail for us to do the problem. So when we think about our tank, we're going to take the vertical distance here to be y, and then we've got a very simple situation. For instance, at this point, if we're going to empty only half of the tank, we're just going to run from 2 to 4. So the half of the tank that we're interested in removing is what's on top. So this will be gone. How do we compute the work to do that? So we first start with this, and then the schematic's going to work for both parts. when you take the y here, and it doesn't matter where it is, we just need a picture. You look at this and say, okay, well, for the y, we're going to have a little strip that runs along y, a little bit above and below. And then, of course, it's going to run through the entire tank. Okay, so we have the surface that's associated with y, and then we have a thickness. So we get basically a geometric solid there. And so, as I like to refer to this, we have a slab of liquid, okay? And so if we have a particular y, we need to figure out how to move that infinitesimal slab to the point that's been prescribed in the problem, and in this case, to the top of the tank. So first of all, once we notate the y here, we can just see now to the top of the tank, that distance would just be 4 minus the variable y. And of course, we can see now that the difference between the two parts of this problem are simply limits of integration, which makes them actually quite straightforward. So now, how does this compare to the chain? Well, now instead of just a linear delta y, just one-dimensional problem, we have a three-dimensional problem. So we have a delta v, that is, we have an infinitesimal volume element. Okay, so we do just like we did in our general mathematics course. And what do we call that? Foundations of Mathematics. We have 5 times 4 times the delta y. That's just a geometric solid. So that gives us a delta v of 20 delta y. You can use any letters you want. And what I'm using is certainly not unique. You want to use other letters, fine. I'm trying to use simple ones where these letters denote exactly what they're describing. Now the force, again, just go ahead and write the weight density of the water in terms of rho. So we take the volume and multiply it by rho. Put the rho anywhere you like. I just put it there because it looks better. So we have 20 rho delta y. That's the force associated with delta v. And then you're thinking, what's the work associated? Well, you take the force and you multiply it by the distance. So the setup here is very straightforward. And that's why I wanted to go ahead and write these out so you could see all of this in action and compare what you've done in your previous problems. Now notice, and I've set this up in a way that's very similar to how I've been teaching you. We simply have work. We want to empty the top of the tank, top half, so to speak. So y runs from 2 to 4. That gives us our limits of integration. And then we just simply put in the delta w here. We have the 20 rho 4 minus y dy. Now, what we want to do here is make this table ready, but we don't want to work too hard because this is a very simple integral. You know, sometimes I look at the problems we've already done and I'm thinking, well, we were kind of stuck with that method. But notice here, we have a very nice interplay with the algebra. So first you're thinking, well, you know, the 20 and the rho, we could just kind of get those out of the way and look for a big G that's only worrying about the 4 minus y. Well, notice the 4 is not a problem, but the minus y is an issue because we don't have a negative dy here, we just have a dy. So to make this table ready, we simply put in the negative here for the negative y to get the right differential and then pay for it here. So that makes a table ready situation. So now, of course, now when we do this to get our, if you want to think of this as a u du, we just add 1 divided by the new power. So we have our 4 minus y squared divided by 2. That's our big G. And sometimes I'll change the limits, sometimes I won't. I mean, it just depends on how you feel when you do it. Well, notice here, it's just sometimes simple to think of it that way. So we've got our G here. G of 4, of course, just absorbs, we get 0. And G of 2 will just, in this case, notice, and I think what you have to look at here when you write things this way, you can see that all the algebra is done for you, and you don't have to do the additional work because of the way it's set up. Where there goes my electricity. Okay, so now we put in the 2, we just get a 2 squared over 2. The 2's absorbed and we get a 2. So now we go back to the original problem, remembering the negative 20 row. So we have G of 4 minus G of 2. So that's just 0 minus the 2, which I've written here. So now you just see the the negatives absorb, and we just get a 40 row. Now that's fine right there. That symbolizes the amount of work. So the only thing that you have to do here, so let's just say, we just say that's a good response, but we have clients. So now we go back to our number. That is, what does rho represent? Well, it's 62.4 pounds per cubic foot. So we simply replace rho with that. And then, of course, what's nice about this, the decimal here will just absorb the 0 there. So we just get 4 times 624. Your homework does not ask you to round anything, so you just compute it as it is. And then, of course, here multiplying by 4 is very easy. We get 2,496 foot-pounds. So again, the procedure is just like we worked with the chain. We simply now, instead of having a linear dimension, we have a 3-dimensional slab, so to speak. And it's very simple. Again, don't worry that you won't have the mechanics to do these problems. The geometry will always be something that you can understand. Now, when we want to do all of the tank, the only difference here between these two problems, again, will be our limits of integration. So here we simply take y to be in the interval 0 to 4. Everything else is the same. Notice this integral and this integral only differ here in the lower limit. So we can just use everything we have right here. We don't have to do anything fancy. Of course, we do the same thing we've done before. The integral's the same. The limits are just different. So we can just move from this point to this point. You can see here, this just mirrors what I've got right here. The only difference now, the G of 4, again, is the same. We just need G of 0. So when we do G of 0, we just get 4 squared over 2. Again, the 2 will absorb into the one of the 4s, and that'll just leave us with an 8. So the only difference between the problems is, again, here we have the -2, here we have the -8. So instead of a 40 row, we get, in this particular case, a 160 row. That's it. And so now, again, we want to figure out what we can tell our clients so they'll not fire us. And so, again, the decimal here will absorb the 0 here. We get a 16 times a 624. You can break that into 2 pieces, a 6 and a 10, to get 6240. And then 6 times 624 will be 3,744. Add that up, you've got 9,984 foot-pounds. So again, these problems will not be as taxing as some of the problems that you saw on your first test. The arithmetic here will probably not be as complicated as what you sometimes see with the washer method or the shell method. You know, those are notorious. And even as you've noticed in some of the notes, the cross-section method can give you some really daunting arithmetic because it just never stops. And so this is one reason I try to break down the arithmetic into steps that are easy to check. And again, you have to be the person who decides what you like best. Now, just remember, there's so many examples here. We don't begin to exhaust any. There will be some other examples that I have in the notes that you should also look through, and you'll see that the technique is exactly the same. Do not forget about geometry of integrals. You know, an odd function on a symmetric interval, integrated on a symmetric interval, gives 0. You can use the evenness where you replace the lower limit with 0 and multiply by 2. Again, the even function on the symmetric interval. You can replace the lower limit with 0 and multiply the result by 2. Again, those strategies are very useful and very time-saving. Don't forget about those because you will certainly see them again. Now, Professor Wallace loves similar triangles. I mean, we take our geometry for granted, and we notice that Without it, we would struggle with pretty much every problem we do. So that is exactly why you have to learn geometry and basic number theory before you take calculus. So this problem, notice we have some geometry. You know, what's our favorite three-dimensional figure right now? It's the cone, the right circular cone. And then, of course, that's how we found the area of the frustum just through elementary means. And boy, was that useful, especially when we want to find the area of a surface of revolution. Again, just remember, all of this will be generalized in Cal 3. Now, for this tank, again, we have a right circular cone. Here are the dimensions that are given in your homework. You have 8 feet across, so that means the radius is 4, and you have a height of 6 feet. Okay, now it's important to realize what you actually do in the problem. It says water is pumped in through the bottom of the tank. So the source is down here, okay? You're not having to do any work to get the water to the tank. It's right at the bottom, okay? So that's where the source is, right here. So it's important that you note that, because that'll be very important as to how you set up your system of coordinates. So now what we can think, it says compute the work to fill the tank. Now notice here, there's another part that you're going to have in your homework. And so I put this as the first part. So I think might be what they do. They just change up the limits of integration. So be ready for that when you work that. So I worked here the first part. So it says compute the work to fill the tank to a level of 5 feet. Okay, again, the source of the water is at the bottom, and the tank will fill in this direction. So that gives you some arithmetic with the coordinates. So we can just go ahead and set the vertical axis to be y. Now notice one thing that's interesting about this. If we have to fill to a depth of 5, we can just take y to be in the closed interval 0 to 5. And then, of course, we're dealing with water, okay? So the weight density, 62.4 pounds per cubic foot. Again, we will call that rho and deal with that as we need to. So notice, and this is important, let's just think of the scenario of what we're doing. As you start to you start the flow of water into the tank, it just moves up, just like in the shape of the right circular cone. Okay, and you're thinking, wait a minute, okay, it's not the box like we had before. How's that going to affect the geometry? Well, now as the water moves up, the slabs, instead of being rectangular, they're going to be circular. So again, you just think of the shape of the tank to figure out what the volume should be. So, and it's very simple. This goes right back to cross sections. So now what you do, when you take your y, you think of extending to the sides of the tank. And you have a little delta y, because again, you want to think of a subinterval from the partition. And then you think the surface of that particular slab will just be that of a disc, of a circular disc. So now you're thinking, I've got the area of the disc times the delta y. That will give me the delta v. So when you look at this, you're thinking, what am I going to do? Well, I've got triangles here, and this is the way I've tried to write this so it's very clear. So notice here, we have 4 from the given, and then now we have what? We have our slab at a height of y units. And now, of course, we can just call the radial distance here x, just our favorite variable. So now we have a radius here of x for the smaller triangle, and then a height, in this case, of y. For the larger one, we have the height of 6, and we have the radius of 4. So now you can just use your similar triangles. So if you like, and it's very simple. It's not a matter of saying, okay, well, if I do it this way, what is going to be the result of the situation. So now let's just look at this. Notice here, and how you set up these ratios is completely up to you. What I did here is I took ratio of corresponding radii. So now 4:x, these are corresponding radii. And then I did corresponding heights. So 6 to y. Again, 4:x as 6 is to y. And that's what I have here. There is nothing, again, that's unique about this. However you set it up, as long as they are ratios of corresponding sides, the result will be the same. But now, of course, we're moving in the y direction, so the independent variable must be y. So let's just solve for x. So let's just flip the 6 and the x, and that'll just give us x is equal to 4y over 6 when we cross multiply. And then, of course, if you like, you can go ahead and absorb the 2 out of each. So x is just 2y over 3. But that's good because now, in terms of the independent variable, the radial distance, x, is 2y over 3. And so now we know how to write the radius of the given disk. We can apply the formula for the area of a circle and then multiply that by delta y. So now we have pi r squared. Well, you knew a pi was going to come into the calculation eventually. So we have pi r squared. So think of the x as the r. So 2y over 3 quantity squared times delta y. Now, when you square out everything, the 2 becomes the 4, the 3 becomes the 9. We've got a y squared, we've got a pi, and then the delta y. And that's it. Very simple, but very important. So again, we find when we're dealing with right circular cones, we know we're going to have similar triangles because the cross sections through the axis are triangles. So that's pretty much a given. You know, if you ever tutor someone in calculus, always do some similar triangle problems just to make sure they remember it. So they're not afraid of it. It's not difficult. It's just something you don't always use very often. And then, of course, you don't feel any confidence with it, kind of like trigonometry. So now we're thinking, okay, well, what's the force? Well, we simply take the delta V and multiply it by the weight density. So we take the delta V here, which is 4y squared pi divided by 9 times delta y, multiply that by rho. So I call it P, sorry, it's a rho. So put the rho anywhere you like, it doesn't matter, we're good. Now, how do we get the delta W? Well, again, this is different from the last problem that we're filling the tank from the bottom and the distance that it's moving is actually just y. No fancy algebra required. So we simply multiply the delta F by the y. So we just now have an additional copy of y. So now we have, instead of a y squared, a y cubed, and everything else is exactly the same. Okay, so that's the hard part, at least in the sense of setting it up. But once you do it a couple of times, it's very simple. So here's our delta W, the infinitesimal amount of work for this particular slab. So we just move this over to the integral. We have, of course, our limits of integration, 0 to 5. Now, if you like, we can go ahead and just extract all of the constants. The only thing that's variable is the y cubed. So now what you can do is just write your big G is y to the 4th over 4, extracting all the riffraff to come out here. Your choice, but very simple. So now, and here's what's interesting about this. This is like I've done the last problems. This is like the very first one with the x squared over 2. Notice we have the 4 here that we can extract, and it will absorb the 4 here from the constants. And then we just, of course, will have 5 to the 4th minus 0 to the 4th using the limits of integration. Of course, very simple. So the only thing that survives, now let's just notice here, we've got the rho, we've got the pi and the 9, which we have here. And then, of course, we have 5 to the 4th, which is 25 times 25. So at this point, we have 625 divided by 9. We have rho, which is 62.4 pounds per cubic foot times pi. Now, of course, and this is your choice. Notice here, the digits here are divisible by 3. That is the sum of these numbers is 12. So we can divide that by 3. When you divide 62.4 by 3, you simply just get 20.8. Now, another thing that you'll notice here, and it doesn't really matter so much, but I went ahead and broke up the 625, the pi over 3 I just stuck over here to the side as 600 plus 25 plus 5, because there's really no simple way to get rid of the decimal. But now when you multiply, you can simply absorb the decimal here. So notice at this point, when we start to multiply, and it's very simple, we just have the 600 times the 20.8, and the decimal moving one place will give us 12,480. And then we have the 20 times the 20.8, but notice in this case, that just gives us 416. So again, in both cases, the decimal is eradicated. Again, we'll take what we can get. And then, of course, here we have the 5 times the 20.8. And of course, 5 times 8 is 40. Again, 0 helps us out. And as you noticed here, I've got the 104.0, which is just 104. So you add the 416 and the 104, that'll give you a 520. You add the 12,480. And so when you sum these two, that gives you a nice round number. 520 plus 480 is just 1,000. So that gives you 13,000 pi divided by 3. Now, of course, I used my Google here. The problem did not ask for exact. Of course, on the test, I probably want you to give me that because that's a beautiful answer, and it's something that you can easily store. Now, of course, I went to Google here to get some decimals because I believe your homework asked for 2 decimals. So that would round to, in this case, 13,630, 613.57 foot-pounds. Now again, remember the work units are in the dimension times the unit of force. And so the idea is that it could be a Newton, meter, but in the case the Newton is first instead of the pound, so that's flipped around. When we do the English units, we don't say pound feet. We probably should and be consistent. But you know what? There are conventions that don't always yell consistency. So I'm not really sure why this is the case. I think sometimes when I think about it, it gives me a headache. But this is how we write them in the English units. We do the dimension first, and then of the linear dimension, and then the unit of force second. So just remember that the homework is very helpful because many times it will have the dimensions of what you're computing by the entry box, and that just kind of helps you to realize what you're doing. It certainly helps you in the process here. You don't even have to write the units. If you think about what you're doing, you've got the correct units as you multiply in these processes here. So this is a really nice problem, very straightforward, but take this example as something we've done before where we have the triangles and we utilize the similar triangles to set up for a nice example. Again, this is something we probably did with related rates with a cone. Right circular cone probably brings back all kinds of memories, hopefully good ones. Now, here we go. Well, I don't have to lie to you. Here was the B part, and I actually did the B part. So you don't have to do this. You're good. Now, the B part was fill the tank from a depth of 3 to 6. See, that's what I was saying before. I don't even need to bother to do this. That just changes the limits from 3 to 6. That's the only difference here. So everything else is exactly the same. So when you get to here, all of these calculations here are the same. No difference. So we factor the 4, the same thing. We get the pi times rho divided by 9. That's the same thing. And now instead of the 5 to the 4th minus 0 to the 4th, we get 6 to the 4th times 3 to the 4th. But now, of course, we can simplify this. There's a little bit more arithmetic here, but it's not difficult. Notice in this particular case, 6 is just 2 times 3. So you get 3 to the 4th times 2 to the 4th minus 3 to the 4th. So you can go ahead and extract the 81 there. And that just leaves you with what? A 16 minus a 1. Well, that's simple. Now, of course, the 3 squared absorbs into the 3 to the 4th to give you 3 squared. And then, of course, 16 minus 1 is 15. So we have 9 times 15. 9 times 15 is 135. So you have pi rho 135. And then, of course, now you do your 62.4. And then, of course, all I did, just like I did before, was break this down, the 135 into 130 and 5, and use 62.4. And that will give me, just like we had before, some nice numbers with no decimals left. So you'll get the 6,240 when you multiply this by 100. That's the easy one. And then 30 times the 62.4, you can do that linearly. Will give you 1872. And then, of course, the 5, 4 times 5 is 20. You got your 0. So you get 312.0. So again, simple numbers that you can add up. And then that will give you an exact value of 8,424 pi foot-pounds. And then, of course, I use my Google here to round to 2 decimals. So 26,464.78 foot-pounds. Well, of course, your clients are going to be more helpful to this, but if they took some, geometry, they know what a good approximation of pi is. But again, that was that. I thought I had not done it, but there you go. This just simply should remind you of the fact that you don't take this lightly, but you certainly want to capitalize on the fact of all the work you've done. And clearly you don't have to start over. You just use a punchline that you already have, and you're done with the problem. So in many cases, all it is merely changing the limits of integration. And again, you think about formulas that you develop when you're trying to have models, that you have predictors that you learn about in college algebra and pre-cal, and then when you get to Cal 1, you can prove the growth and decay law, you can prove the logistic equation, and you can see how it's nice to have a way to substitute values to predict values. And here, of course, this gives us the predictions for the work, which can be very helpful. Now, the very last problem I thought was kind of interesting, and I thought about it. I changed up the way I was going to present this, and then I think I came up with something that works. This is, like I said, when you look at the notes, there's an example of a cylindrical tank that you use to fill a tractor, and it's written up very nicely. Again, go through that. Those are just more geometry where you apply the same process, but I want you to get grounded with these. Then you can look at that one and feel comfortable about it. Just remember, you need the distance that the slab or whatever geometric piece has to move, okay, in order to calculate work. And so that means you need to figure out what it is you're doing. Are you emptying the tank? Are you filling the tank? Where's the source? All these items do make a difference as to how you set up your coordinates and your algebra. But again, usually very straightforward when you compare it to what you've already been doing. Now, this is a WebAssign problem that I found to be very good, because the problem itself gives you a good hint, because this is not a trivial problem. When I think about it, the problems we've done and the problems I just talked about are fairly straightforward in their strategies. This one is not so much. I mean, this requires a little bit of thought, and the way I set it up hopefully will make it more understandable. But the hint that the homework does provide is a good one, okay? So this is a very interesting problem, and I think you will enjoy it. How does it differ from the first problem I did? Well, we have a 15-foot hanging chain, which has a linear density of 3 pounds per foot. Remember, the first problem was 4 pounds per foot, and it had a weight of 500 pounds on the bottom. So we had to divide the constant force, into two cases, a constant force and a variable force. Well, this problem is different. Okay, what it does, it says the bottom of the chain is lifted to the 15-foot level. That is, you've got the chain hanging, thinking it just, right hits the ground. It's not, there's no slack or anything. It just straight all the way to the ground. It's a 15-foot chain, and it's set up so that you've got that linear dimension, no slack and no wobbling or anything, straight down. And you take the bottom of the chain and you pull it up to the very top to where you get this U shape. So as I've said here, you double the chain. It says the bottom of the chain is lifted to the 15-foot level, leaving the chain double. Okay, you think about that. We do things like that. You think about hanging Christmas decorations or whatever. You don't think about the physics, but yeah, that's something you can imagine. You can think of doing something where you had a loop, so to speak, a U-type shape like that. Okay. Now, again, this is idealized, but it's a good problem. So what it says compute the work, and you're thinking, I have no idea what to do. Well, what I thought was interesting about the problem is they gave you this hint. They didn't give you the delta Y, but they did think of taking a Y at least somewhere. They didn't tell you where the Y was, but they gave you the dimension of Y in the two places. And then, of course, that gives you what the dimension in between would be. So let me show you how to work this problem in a way that will make sense, and then you can share it with your friends and see what they think about the strategy. So again, think about this. The part, halfway up, that's not going anywhere. That's just going to be right here. Okay, but the halfway down, that part's going to move up. And then there'll just kind of be a piece at 15/2 that just stays stagnant. It's not moving anywhere. It's just going to be like the linchpin, so to speak, the fulcrum. Okay. So what I've done is I'll say take Y in the closed bounded set 0 to 15/2, half the length of the chain. And we want to move the piece of the chain, which is I call delta Y here, a distance that it's going to have to go. So here's the thing. If you take a Y and you think about taking the chain where now the Y is the bottom, like I've written here. And here's where the hint is. Then you're thinking you've got the Y also duplicated up here. Because now you're thinking, well, how far is this going to have to go? Well, this piece right here, delta Y, will move a distance 15 minus 2Y. If we call this the Y, as I've notated here, and then take a little sliver, it will move that distance. It won't go any higher than that because the chain is going to be double. It's not going to be bunched up. It's just going to be double. And so this is what your homework gives you. But they just say a little bit. They don't say why they did this, but it is a good hint. So now you think, okay, the length of the delta L is just the delta Y. And then as I've just said, this little delta Y will have to go this distance so that this meshes with this. Again, you can't just keep going and bunch up the chain. So now you're thinking, okay, well, that little sliver here will have a force rho times delta Y. And then the work will just be the force times the distance. So that hint that you get in your problem is actually very important, but it's only maybe a third of the problem. You've got to be able to analyze it. So I think this is a really, really good problem. So now, again, when you think about it in terms of the calculus and you take the hint, then you can do variations on this problem. You can change up some of the geometry and have a good time with it. But now with that aside, and that I'm, excited about the problem being really neat, we can now say, okay, well, the work we can now sum using an integral from 0 to 15 over 2, and then we've got rho 15 minus 2y dy. Now, what I did over here is I did the same thing. Just go ahead and factor the rho. The rest of the stuff is not riffraff. So what you can do, you can think, well, can we do this like the other one and fix it up and do all that? Well, I didn't do it that way, and I could have. You could, again, you could fix this. You do the -2 here and do the -1/2, and then just do the 15 minus 2y quantity squared divided by 2. You could do that exactly that way. I didn't do it. I mean, it's funny that I didn't. I don't really know why, but that would make it just as easy. Well, let me just show you what I did here. Notice when you look at this and you think about, okay, how do we do this problem? So now when you look at this, you've got just doing it piecemeal. Say you're in calculus 1 and you're not being all, elegant in your method because you haven't listened to Professor Allis give you this nice technique. So you think, okay, well, I got it. I just got 15y minus y squared, the 2 absorbing here with the 2 with the antiderivative. So you're thinking, if I did it this way, it wouldn't be a big deal. And here's why it wouldn't be a big deal, because the algebra here is simple. And I think when I looked at it, I thought, well, no big deal. I'll just do it the way it is. So just remember, functions possessing the same derivative differ by a constant, okay? They're not necessarily the same. And that's the uniqueness or the unique quality of antiderivatives. They're clearly not unique. I mean, but they are unique in the sense that when you discuss them, they have very particular qualities. So now all I did was factor the y, and it's just easy to do. So first we have what? F of 15 over 2. Well, 15 minus half of it is just half of it, so whatever. And then 0, of course, we get a 0. So now when you look at this, you just got 15 squared divided by 2 squared, which is 225 over 4. So again, that I did it differently should just make you understand that you are always in control, not Professor Allis, and so you can do it the way you want to. So now notice, and we look at this, the rho here is just 3, right? And so now we have 3, g of 15 over 2 minus g of 0. And it's so sad. I fixed the g, but I didn't fix the other g's. Of course, you heard me say g. How sad. These are g's, obviously. How funny. Yeah, you all would be sitting in class, Professor Ron, isn't that a G? It looks like an F, but you called it a G, so it shouldn't be a G. Absolutely. So funny, right? So now when we look at this, we just have what? 3 times 225 over 4. Of course, these, 4 and 225 and 3 are all relatively prime. So now WebAssign doesn't say do anything about an approximation. So we could divide into this or do this, your choice. I just decided to multiply that because it was easy. And then you can divide 4 into 6 to get 1. Then that gives you a 27. And then you can keep going to get the 6. And then that gives you what's left here. Let's see, we've got 4 into 6 gives us 1. That gives us a 27. 4 into 27 will give us 6, leaving a 35. Oh, 35. Okay. So yeah, it's not exact. So we get, if it was bumped up to 36, we'd be fine. So we get a remainder of 3 and a half, so to speak. Here, let me just write this out. I'm confusing everybody by the way I'm writing this. Let's just say we're in general math. That's fascinating. So if you're teaching someone to divide, you'd say, okay, well, this is 4 into 6. We'll go 1 time. And then that leaves you with a 27, 6 times. And then the 35. Okay, so you think 4 goes into that 8 times. Then plus the remainder divided by the divisor. So that's what I was trying to say, but it didn't come out very well. So when we think about number theory, we're thinking this is kind of like doing the division algorithm in pre-cal. It's a very important result. You think about, how do I write the result? You can say P of X equals the quotient times X times the divisor plus the remainder. That's one way to write it. But one way that we really like, which is like this, is we just go ahead and divide by the divisor. So we say P of X divided by Q of X equals, here now we've got the quotient plus the remainder divided by the divisor. And I'll get the D right here. So this is why calculus is just fancy arithmetic. I mean, when you think about this, everybody, again, when you teach someone calculus, you remind them about number theory. And so this is exactly why we get what we get here. And so now, if we want to be lazy, we just write that as 168.75. For some reason, I thought this came out exactly when I looked, but of course it's not. That's an odd number, that's an even number. It's not going to be exact. But what's interesting about this is that when you teach someone about the division algorithm for integers and the division algorithm for polynomials, there is no difference. Only the names have been changed. Of course, when you actually do the proofs, there's some nuances that you have to introduce to deal with the fact that you've got a polynomial. But really, when you think about it, polynomials are so well structured. And when you think about numbers and how they work in our base 10 number system, it all comes together number theoretical. So when I say that mathematics is just what? Fancy arithmetic, that is actually very true. All these famous people, intelligent people, were always computing, figuring out how to supply the correct arithmetic to get the right result. And so when we think about this problem, it's always easy just to punch on the calculator. But when you think about it, the calculator takes away a lot of the process you need to do with your brain. And I've got students who compute very well. But again, when I write a recommendation for someone to go to the tutoring center, I'll say, be sure to teach them, okay? Don't use a calculator. Put the calculator aside and say, okay, if you need an approximation, let's go to Google and click it in. And then when we get to the infinite series, we're going to figure out how the calculator works. But again, just think about this problem and notice that it's not very intuitive what we get here in terms of a response. That's one thing about calculus. You can't just look at it and say, oh, that's the antiderivative, that's obvious. Or that's the answer, that's obvious. It's not. The arithmetic is hardly elementary, even though we're still working with so-called elementary functions. As I said before, when we do integrations and we try to compute arc lengths, we find that we run up against a problem, as I said in lecture, when we try to compute the arc length of the cosine function, just from maybe 0 to pi over 4. We don't get an integral that abides by standard trigonometry. And as I said before, it stands by or is basically solved using an elliptic trigonometry, an elliptic function. I mean, amazing. I mean, truly, you think about it. I mean, we can't look at anything that we do and just say, oh, that's easy. It's easy once you understand it, but then you have to look at a different set of functions that will solve the problem. Remember from Cal 1 when we started talking about hyperbolic functions. Those functions are actually solutions to differential equations, which are the same for the elliptic functions. But the neat thing about the elliptic function is that we know the connection between the circle and the ellipse, one being a generalization of the other. But with the hyperbolic, we thought, okay, well, we've got these new objects, and we saw how they mimic the standard trig functions. Well, and we could see how the elliptic functions actually mimic the standard trig functions. The trig functions that we learn about in geometry and pre-cal as being the standard. So just remember every time we come into a different problem where we have to invent something new, we need more arithmetic. You know, we have the complex numbers, we have complex analysis. So when you look at the work problems, it's not like we're, you know, I'm getting off on a tangent here. It's not like we're having to create a lot of new mathematics, but we certainly appreciate the mathematics that we have learned in order to do these problems. So go back through this problem and realize the hint that the homework gives you is actually quite useful in how you can now pattern a solution that ties in with the ones that we've already done. Okay, so hopefully as you do this, you'll enjoy this. The homework is not very long. Please, as I said before, go back through the lecture notes that are online to see some additional examples and practice, and go back and do some of the problems that you've done that you had for your first test to see how the arithmetic is very similar. Okay, well, as I say, what do you do today? And then, of course, Andrew, Aiden, and Alex would say, yeah, we need to talk math and we need to share our knowledge. So please be sure to do that. You all have a great day.